At this point, you might wonder why we care about the moment generating function of a chi-square distribution. And now let me explain to you why. If you look at the distribution of a chi-square random variable, can you compute its probability distribution function? I guess it is very hard. But what can we do if we cannot compute the probability distribution function of a random variable? What we can do instead is that maybe we can give an estimate of how this random variable is concentrated around its mean. What is the mean of x? Namely, what is the expectation of x? The expectation of x is equal to so we just plug in the definition. So it will be sum of the k expectations of the squared standard normal random variables. And you know, for a standard random variable, each of them will be equal to 1. So it will be sum of k many ones, which is k. So we'll be interested to know how well x will be concentrated around k. And we expect that when t is large, this guy will be close to 1. And in probability theory, an inequality giving an estimate of this is usually called a concentration inequality. And in fact, we're going to prove the following concentration inequality for the chi-square distribution. Let's call it lemma 1. Let Q be a random variable following a chi-square distribution with k degrees of freedom. Then, for any epsilon between 0 and 1/2, the following inequality holds. The probability of Q concentrated between 1 minus epsilon times k and 1 plus epsilon times k is bounded below by something very close to 1. When our epsilon is small. So if you move this k to the middle, so you get q minus k between negative epsilon k and plus epsilon k has probability very close to 1 as epsilon close to 0, which gives a concentration inequality for a chi-square distribution Q. And now I can answer the question why we care about the moment generating function of chi-square distribution. That is because in the proof of such inequalities, one very important technique is by the moment generating function. What we are going to do is that we're going to take the exponential of all sides and use the classical inequalities probability like Markov inequality to give an estimate. That is the classical trick in proving concentration inequalities. Now we are going to formally prove this. Note that this is a two-sided inequality. We're going to prove that the probability of this Q not falling into this interval will be bounded by twice of this. To look at the complement, we're going to first look at the case when Q is greater than 1 plus epsilon times K. To bound this probability, we're going to use the moment generating function method, as I mentioned. Specifically, we're going to first take the exponential of lambda times Q and the exponential of lambda times 1 plus epsilon times K. And this inequality holds whenever lambda is non-negative. Now, by the Markov inequality, this is less than or equal to the expectation divided by this guy. So this is by Markov's inequality. Now, what is the numerator? The numerator is precisely the moment generating function. As we computed, it is 1 minus 2 lambda raised to the power negative k divided by 2. This is true whenever lambda is between 0 and 1/2. Now let f of lambda is a function when the numerator you get 1 minus 2 lambda raised to the power negative k divided by 2. And the denominator exp of lambda times 1 plus epsilon times k. So what we did is that we wrote this as a function of lambda. We fixed parameters k and epsilon, and we view this as a function of lambda. We are interested to know the minimum value of this function in terms of lambda. This is a typical calculus 1 problem, finding a minimality of a function. Because this function is differentiable, we'll simply take the derivative with respect to the variable lambda. Simplifying this yields when lambda is very close to 0, this will become something close to k minus 1 plus epsilon times k, which is a negative term. So this thing will be negative. As lambda increases, this guy will become bigger. When lambda is very close to 1/2 from the left, this guy is very, very big. Will be bigger than this, 1 plus epsilon times k. So this f prime of lambda is negative when lambda is close to 0, and it becomes positive when lambda is close to 1/2. And there's a point where it vanishes. That critical point, if you solve this equal to 0, you get that when lambda is equal to epsilon over twice of 1 plus epsilon, this derivative vanishes. So when lambda is from 0 to this critical point, f prime of lambda is negative. And when lambda is between epsilon over twice of 1 plus epsilon and 1/2, this derivative is positive. And correspondingly, f of lambda is monotonically decreasing on the interval from 0 to epsilon over twice of 1 plus epsilon, and monotonically increasing on the interval from this number to 1/2. And here, to guarantee that this number is less than 1/2, we need epsilon is less than 1. But that is guaranteed by our assumption. We assume epsilon is less than 1/2. So this number is really less than 1/2. Okay, now we can optimize this to its minimum by taking lambda equal to this number. So when we plug in this number, we're going to get after simplification, this quantity. So combining this and the inequality that this probability is less than or equal to this guy for any lambda between 0 and 1/2, we obtain that this probability is less than or equal to 1 plus epsilon divided by exp of epsilon raised to power k divided by 2. Now, we're going to use Taylor expansion to further simplify this. The goal is to combine this numerator and denominator. To this end, we make the following claim. We claim for epsilon between 0 and 1/2, 1 plus epsilon is less than or equal to exp of epsilon minus epsilon squared minus epsilon cubed divided by 2, this inequality. This inequality can be verified by first taking the log of both sides. This is equivalent to saying that log of 1 plus epsilon less than or equal to epsilon minus this. And now you consider the Taylor expansion of log of 1 plus epsilon. It is epsilon minus epsilon squared divided by 2 plus epsilon cubed divided by 3 minus epsilon to the 4th power divided by 4, etc. Less than or equal to, let's copy this down. And this guy is further equivalent to, if you cancel this term, this term, this term, this term, the last thing is apparently true, because the left-hand side is less than epsilon cubed divided by 3 but the right hand side is bigger than this number. So the last inequality is apparently true. So you go all the way back and get this claim. Now under this claim, if you plug this inequality back to here, you obtain P of Q greater than 1 plus epsilon times K is less than or equal to. Now this EXP of epsilon cancels with EXP of epsilon, less than this. Okay, so we have given a bound of the probability when Q is greater than 1 plus epsilon K by this. That basically finishes half of this inequality. Now it suffices to show that the probability of Q less than left hand side is also less than the same thing. So, on the other hand, this probability of Q less than 1 minus epsilon times K what we do now is that we're gonna take the exponential again. But instead, this time we're gonna take EXP of negative lambda, so that this inequality is flipped. So this is true for any lambda greater or equal to 0, or negative lambda less than or equal to 0. The reason we do this, the reason we want to flip this inequality is that we want to use the Markov inequality. So we would like to see the inequality in this direction. And now we use all the results for the modern generating function of a chi-square distribution again. This is a chi-square distribution with k degrees of freedom. So in the numerator we get 1 plus 2 lambda raised to the power negative k over 2. Of course, in this situation, because lambda is greater or equal to 0, negative lambda is less than or equal to 0, this is well defined. If you don't like this negative sign, you can flip this quotient. Now, for this quotient, we're going to do our optimization again. This time, I'm not going to take the derivative. It's really complicated and also not really necessary. You just look at this quotient and see what lambda do you want to take. And you compare this situation with our previous situation. You compare them. Previously, we take lambda equal to epsilon divided by 2 times 1 plus epsilon. Now by symmetry, you should expect this time that we take lambda equal to epsilon divided by 2 times 1 minus epsilon. This is what we want to do. Of course, you can take the derivative with respect to lambda, but you can also do it just with a smart observation. This lambda is apparently greater than 0 because epsilon is less than 1/2, in particular less than 1. So you plug this in, what you get is, and with simplification, you pull out this k over 2. Now, like we did before, we would like to simplify this guy. We want to turn this into exponential of something. To make this look simpler, this time we make this claim. We claim that 1 over epsilon is greater or equal to exp of epsilon plus epsilon squared minus epsilon cubed divided by 2. This can also be checked with Taylor expansion, because this inequality is equivalent to, if you take a log, and you consider the Taylor expansion of the left-hand side, which is epsilon plus epsilon squared divided by 2 plus epsilon cubed divided by 3 plus dot dot. This inequality is apparently true. So this claim holds. Therefore, you can majorize this to this quotient, and you see that e to the epsilon cancels with e to the epsilon. This gives you exp of negative k times epsilon squared minus epsilon cubed divided by 4. Okay. Now you combine this with this. What do you get? We get the probability of the union of two events. One is q greater than 1 plus epsilon times k. The other event is q less than 1 minus epsilon times k. This probability will be less than or equal to, and we take the union bound, so there will be twice of exp of negative k times epsilon squared minus epsilon cubed divided by 4. And if we take the complement, this is probability of q lying between 1 minus epsilon times k and 1 plus epsilon times k greater or equal to 1 minus twice of exp of negative k times epsilon squared minus epsilon cubed divided by 4. And now we are done with the proof of this lemma. The proof is not too tricky. The only smart idea we used is taking the exponential function. The rest is quite routine.